So number 4, initial speed on a hilly path. So it's obviously conservation of energy. And starts with the minimum initial speed, so it passes the 9-meter hill at point A. So if it's the minimum speed, that means that the kinetic energy at the top is 0. It's kind of just a agreed convention in physics that the minimum speed means, well, it's not just an agreed convention. It makes sense that if it's the minimum speed, then it just barely reaches the top of the hill. If it were going faster, then it would reach the top of the hill and then be going fast. And so to barely make it to the top of the hill and pass it, then you have to barely make it with 0-ish energy, kinetic energy, at the top of that hill. So to draw that, so you see I have this height at the top of the hill, and the initial kinetic energy is labeled, whatever that is. The final kinetic energy is 0. And this gives us, you start with the, I believe Dr. Hager calls it the Hager's all-purpose energy equation, HAPEE. And this is pretty useful for most problems. In this case, you set, as I said, the final kinetic energy equal to 0 because it's not moving there, and the initial potential is 0 because the height is initially 0. This gives a really nice simple equation, and you plug in the usual and you can cancel the mass if you want. And you can find that needed energy. The needed velocity, which of course matches up to the needed energy. Part B. The initial speed is now 20 meters per second instead of whatever you found in part A. What is the speed when it reaches point B? Well, it's going to be exactly what it started with because there's no friction, and so it goes up the hill, comes down the hill, but it gains back the same speed that it lost on the way up the hill. So that was easy. C. What about when it reaches point C? So it goes through some friction. Do we have the coefficient of friction? Yes. Kinetic friction. So this is very nice because it's only a part of the problem instead of combined as it was with the skiing. So you do the same as before, force times the distance. There's no angle involved because it's going exactly in opposite the direction of motion. And the force of friction is mu Fn, mu times normal force. And so mu is given, might be 0.43, okay. And normal force is just mg because it's flat and there's nothing else going on. And the distance is probably given. Yes, 12-meter long stretch. So that's how much energy is taken away. So we have the initial kinetic energy, take away that friction, and you get the final kinetic energy, which actually comes from the same equation that we used before, which is that one with friction thrown in. I showed it in the previous problem. Potential energy isn't changing here, so it doesn't show up in the equation. You could say it's 0 on both sides. So you find kinetic energy final. You find velocity final, because that would be 1/2 mv squared. And that's it. Maximum height it can reach. And exactly the same as part A of the problem. Only you're using this kinetic energy that you just found for part C and solving for H.